Hi and welcome to the second part of a video series on LINQ. This video is also the second part of the 7th tutorial in an advanced C# course. LINQ stands for Language Integrated Query. In the first part of this video series, we looked at an overview of LINQ. We discussed that LINQ is the name for a set of technologies based on the integration of query capabilities directly into the C# language. In this video, we'll demonstrate examples where we'll create LINQ queries using method syntax and subsequently show how we can express the same LINQ query using query syntax. As discussed in the previous video, in this series, query syntax is recommended because the logic within the query syntax is easier to read. In this video, we'll look at code examples using the following LINQ operators: select, where, join, and group join. We'll discuss what is meant by method chaining and demonstrate an example that makes use of method chaining in the context of a LINQ query. We'll look at what is meant by deferred execution of LINQ queries and what is meant by immediate execution of LINQ queries. We'll discuss the inherent advantages of deferred execution in the context of LINQ. To further clarify our understanding of deferred execution, we'll create a code example where we'll implement deferred execution for our own custom extension method for an IEnumerable type. We'll demonstrate how the C# yield keyword is implemented in the relevant code example as part of code to implement deferred execution. At the end of the tutorial, we'll look at the join operator and the group join operator. We'll create code examples to help clarify our understanding of these two LINQ operators. In the first part of this video series, we discussed that extension methods and lambda expressions are fundamental to how LINQ works. We created our own extension method for filtering a generic list that can be strongly typed with any C# type, including user-defined types. We then demonstrated how a lambda expression can be created in calling client code, which enables the calling client code to determine how the relevant list of data must be filtered. The reason we created our own filter extension method was to help us understand the fundamentals of LINQ. LINQ functionality is encapsulated in two static classes that are members of the system.link namespace. These two static classes are named queryable and enumerable. These classes mostly contain extension methods As with the previous video in this series, I'm going to demonstrate the code examples in this video on my Mac platform. If you are using a Windows platform, the fact that I'm using Visual Studio for Mac should not be a barrier to follow along with these code examples. The code creation process is almost exactly the same experience when compared to implementing the same code using Visual Studio for Windows. So let's create a .NET Core console project. Let's name this project LINQ Examples _1. So to save time, let's copy data-related code that we created in the previous video of this series from the appropriate GitHub repository. So please navigate to this URL in your browser to access the relevant GitHub repository. As always, all URLs referred to in these videos can be accessed through appropriate links included below in the description. So let's copy the data-related functionality from this repository to the project we have just created. So in your browser window, click the directory icon labeled TCP data, like this. Click the class icon labeled employee. Let's copy the code for the employee class from this page to our clipboards, like this. And simply paste the contents of the clipboard below the program class in our new project. Let's also copy the code for the department class like this to our clipboards and paste the contents of our clipboards below the employee class within our new project. Let's then copy the code in the data class to our clipboards. Then paste the contents of our clipboards below the department class in our new project like this. So we have some red squiggly lines within our data class. To fix this, let's include a directive to the system.collections.generic namespace at the top of our code, like this. We are just creating throwaway code in this video to help us understand the relevant topics discussed in this video. So we are not too concerned with code neatness in this video. In our main method, let's create a strongly typed generic list that is strongly typed with the employee user-defined type. Let's name our generic list variable employee list. Let's assign the value returned from the data.getEmployees method to the variable we have just named employee list. This line of code will populate the employee list collection with made-up data that was hard-coded in the data class in the previous video of this series. Let's define a generic list that is strongly typed with our department user-defined type. Let's name our variable for this list department list. Let's assign the value returned from the data.getDepartments method to the variable we have just named department list. This will populate the department list collection with made-up data that was hard-coded in the data class in the previous video of this series. So let's create a link query that makes use of the select link operator. In order to use a link operator, we of course need to include a using directive to the system.link namespace. For this query, we want to select everything from the data stored in our employee list collection. We can do this by simply invoking the select method on the employee list object, like this. The select method is an extension method provided to us through link. We can shape our data through the use of a lambda expression like this. We discussed anonymous types in the previous video of this video series. So, the select operator returns an IEnumerable collection of objects. The lambda expression passed into the select extension method provides an instruction on how we wish to shape each item of data within the returned IEnumerable collection. This is specifically expressed through this anonymous type. Anonymous types provide a convenient way to encapsulate a set of read-only properties into a single object without having to explicitly define a type first. You can see how the use of anonymous types can provide the developer with flexibility and convenience when constructing queries. So here we are providing an instruction that we want each item of data in the returned IEnumerable collection to contain a full name property, which is a concatenation of the first name and the last name properties of the relevant employee record, and a property containing the employee's annual salary. So let's write the code to output the results of this query to the console screen. Let's see the code in action. Great! So if we want to filter this data, we can do this by chaining the where extension method to our select operator like this. Method chaining is a common syntax for invoking multiple method calls in C#. Each method returns an object, allowing calls to be chained together in a single statement without requiring variables to store the intermediate results. So the select operation will return an IEnumerable collection object. We can filter this returned IEnumerable collection within the same link query by chaining the where extension method to the select extension method. The where extension method filters the data stored in the IEnumerable object returned from the select method. through a lambda expression passed to the where extension method. The lambda expression provides instructions to the where extension method on how the data must be filtered. Once the data has been filtered through the where extension method, an IEnumerable collection of results is assigned to our results variable. We are then traversing our results using a for each loop and displaying each item in the IEnumerable collection to the console screen. We discussed the var keyword, which allows for local implicit typing within methods in the previous video of this series. Please view the previous video in this series for more details. So here we are implementing link explicitly using the extension methods provided by link. We are using the select operator and the where operator in a link query implemented using method syntax. Let's run the code. Great! We can execute the same functionality using query syntax. So let's comment out the previous code and include a comment to label this code so that we are able to refer to this code later if need be. So let's first implement the link query using query syntax without the where clause. Let's run the code. Great! Let's implement the link query implemented using query syntax, and this time include the where clause within the link query using query syntax. Let's run the code. Excellent. And we get exactly the same result when compared to running the query that we implemented using method syntax. But we have constructed our link code using link query syntax as opposed to using relevant extension methods. The query syntax is more readable, and we don't need to chain our extension methods, as we did in the previous example where we changed the where extension method to the select extension method. Let's take a closer look at our query where we used method syntax versus the same query where we used query syntax. Note that standard query operators in our query syntax are converted into extension methods at compile time. So standard query operators are essentially the same as their counterpart extension methods. Microsoft recommends using query syntax as opposed to directly implementing the relevant extension methods where possible. As discussed, this is due to the readability advantage inherent in the query syntax. There are times when you will need to use extension methods directly where equivalent query syntax is not available. We looked at a few examples of this in the previous video of this series. For example, using aggregate functionality, like for example finding the average, min, or max annual salary for a collection of employee records. We would need to use the respective average, min, or max extension methods to calculate and return the relevant values. The developer is able to execute link queries with deferred execution or immediate execution. So let's first understand what is meant by deferred execution. Deferred execution means that the evaluation of an expression is delayed until its value is required. This improves performance because only necessary executions are carried out, i.e., at the point where the relevant value is required. Let's use our last query example to illustrate this point. So when we first assign the value returned by our query to our results variable, the query is not executed. It is only when we traverse the items in our results variable that the actual execution takes place, i.e., with each iteration of the for each loop, an execution is performed, whereby the relevant item is evaluated and returned from the collection. Another advantage of deferred execution is that an update to the relevant data collection will immediately be reflected in the results. So, for example, let's add a record to our employee collection. Note, the salary for this new employee is above $50,000, so this employee should appear within our results. Let's run the code. And you can see that this is proof that the results are evaluated within the for each loop, and the query itself is not executed at the line of code where the relevant query is located. The execution of the query is deferred until the results are traversed within the relevant for each loop. To further understand the concept of deferred execution, let's create a code example where we'll implement deferred execution for our own custom extension method for an IEnumerable type that is strongly typed as the employee user-defined type. Let's create a static class named enumerable collection extension methods. Let's create a static method within the static class that we have just created, and let's name this method getHighSalariedEmployees. We discussed extension methods in the previous video for this video series. For more information on extension methods, please access a link to this video. As discussed, a link to this video is available below in the description. So let's implement the code for the getHighSalariedEmployees extension method like this. Note the use of the yield keyword. You can use a yield return statement to return each element one at a time. The sequence returned from an iterator method can be consumed by using a for each statement or link query. Each iteration of the for each loop calls the iterator method. When a yield return statement is reached in the iterator method, the relevant value in the IEnumerable collection is returned, and the current location in code is retained. Execution is restarted from that location the next time that the iterator function is called. Let's go to our main method and implement a query that calls our extension method on the employee list collection. Let's copy and paste the code that we have already written to traverse the results and output the relevant data. And let's add another employee record to the employee list collection as we did before. Let's run the code. And you can see that the new employee record is reflected in the results. The results are kept up to date due to deferred execution. Note that deferred execution reevaluates on each execution, which is known as lazy evaluation. The converse of deferred execution is immediate execution. Immediate execution means the relevant query is executed immediately. To execute a query immediately, we need to apply an appropriate to-conversion method to the query. So let's copy the previous code example Let's uncomment the relevant code. Let's change this code so that the query executes immediately. We can use the toList conversion method for this purpose. We are using query syntax here, so in order for us to use the toList conversion method, we first need to wrap the relevant query in brackets, add a dot, and then the toList conversion method. We are explicitly typecasting the IEnumerable value returned from the query to the list type through the implementation of the toList conversion method. We are also executing the query immediately. Let's uncomment the rest of the relevant code for this example. And let's run the code. You can see that the execution of our query is immediate, because this time, after we've added a new employee, the query has not been evaluated again to include the new employee record in the results. This is, of course, why the new employee does not appear within the results output to the screen. This proves that our query has executed immediately at the line of code where the query is located. And remember that query syntax does not support two operators, so we need to wrap our query in brackets, as we have done here, and call whichever to method is appropriate, for example, toList, toArray, or toDictionary. By calling the relevant to method, in this case the toList method, we are causing our query to execute immediately. Without the toConversion method, the relevant query execution would be deferred until the relevant results are iterated. So let's move on to the join operator, and then we'll look at the group join operator and highlight the difference between these two join operations. In the previous video in this series, we looked at the join operator and discussed how we can perform an inner join on two IEnumerable collections using a link query. So here we have two collections that we wish to join. In this specific use case, we need to include a descriptive department name in our results displayed to the user. We only have a department ID field in our employee type, so in order to merge the properties from our employee type with the relevant property from our department type, we need to join records of type department that reside within our department list collection with records of type employee that reside within our employee list collection. We can do this by matching the ID field in the department records that reside in the department list collection with the department ID property of employee records that reside in the employee list collection. We can do this through link by using the join operator. Later, we'll demonstrate a join operation, but using the group join operator. We'll also discuss the differences between the join operator and the group join operator. Let's look at the relationship between the collection of department records with the collection of employee records. Department records have a one-to-many relationship with employee records. A specific department can have many employees as members. A specific employee cannot belong to more than one department at a point in time. Data collections can also have one-to-one relationships with one another, or many-to-many relationships with one another. So in this example, we are going to look at how we can use link to implement a join operation between two collections of records that have a one-to-many relationship with one another, i.e., one department to many employees. So let's implement a query that joins the department list collection with the employee list collection, where the ID property of the relevant objects of type department match the department ID property of the relevant objects of type employee. So the syntax for this link query would look like this, when we implement the join operation using method syntax. So to join department records to appropriate employee records, we can use the join extension method and invoke the extension method on the department list collection. The first argument we need to pass into the join method is the collection on which we want to join the department list collection. So we pass in the employee collection object here. The second argument is the key from the outer collection, the department list collection. So the outer join key is the ID property that resides in the department type. we can express this argument as a lambda expression like this. The third argument is the inner join key, which is the department ID property, which is a member of the employee type. We can express this argument as a lambda expression like this. So we are joining on the ID property, which is a member of the department type, with the department ID property, which is a member of the employee type. We can define an anonymous type where we are able to shape the data for each item in an IEnumerable collection that we want returned from the relevant query. Here we are defining an anonymous type within our link query that includes the employee full name, which is a concatenation of the employee's first name and last name, the employee's annual salary, as well as the relevant department object's long name property. The long name property will give us a descriptive department name in our results. We are including the department type's long name property in the relevant anonymous type. This is the whole point of joining the department list collection with the employee collection, so that we are able to include a descriptive department name within our results. We only have the department ID as a member of our employee type, so if we only returned results from the employee list and wanted to include department information, we would be restricted to the department ID property, which is an integer value and is unlikely to be meaningful to a user. Let's run the code. Great! But as discussed, where it is possible to use query syntax rather than method syntax for our link queries, we should use query syntax because the logic expressed in the relevant query is far easier to read. So let's write the same query using query syntax. As you can see, it is far easier to read, and it is also similar to query languages with which we may already be familiar, for example, Transact SQL. Let's express what a similar query in Transact SQL might look like. So let's imagine that we have a table in a SQL Server database that could map to our employee type. Let's say this table has the same name as our employee type. Let's also imagine that we have a table in the same SQL Server database that contains a table schema that could map to our department type. Let's say this table has the same name as our department type. So the Transact SQL would look something like this. You can see how the from clause, the join clause, and the select clause are implemented in both the link query syntax and the Transact SQL syntax. Even though the link query contains the same clauses in a different order to the comparative clauses in the Transact SQL query, for someone who is familiar with Transact SQL and not necessarily familiar with link query syntax, this link query syntax at a glance should be fairly easy to understand. So the point here is that link query syntax is similar to query syntax with which many of us will already be familiar. So this makes the implementation of link queries using query syntax more intuitive. As discussed, the link query syntax is also more readable than the equivalent link query implemented using method syntax. So the key takeaway here is to use link query syntax rather than method syntax where possible, because it is more intuitive to implement and easier to read. Let's run the code. Great. So let's look at the group join link operator and why we might want to use the group join operator in our link queries. We have just performed an inner join using the join operator. This query will only return those records based on the ID property of relevant objects of the department type in the department list collection, matching with the department ID property of relevant objects of the employee type in the employee list collection. Diagrammatically, an inner join query can be represented like this. What if we wanted to return, through a link query, all the department records in our department list collection and only employee records where the department ID property of employee objects in the employee list collection match the ID property of department records in the department list collection? So if we were to write the Transact SQL version of this query, it would look something like this. We would use a left outer join to achieve the desired result. This query would bring back all department records, but only those employee records where the relevant employee records department ID values match the ID property of the relevant department records. So, diagrammatically, we can represent a left outer join query like this. So let's look at the diagram representing an inner join operation and compare the diagram to the diagram representing the left outer join operation. So let's use our group join operator in a link query to return all department records from the department list collection, but only the employee records from the employee list collection with a department ID property that matches an ID property of a department record in the department list collection. So here we are implementing our query using method syntax. You can see the implementation of the group join operation using method syntax is very similar to the way we implemented the join operation in the previous example. Let's run the code. Note, the way we have structured our output is clearly different when outputting the results of our group join query when compared to the way we structured our output of the results of our join query. But note that at the moment the same join between department records and employee records has occurred. The reason for this is not because the group join and the join operators perform the same type of join operation. It is because currently each of the records in the employee list collection match with a department record in our department list collection. Let's change our data to highlight a key difference in the join operation and the group join operation. Let's do this by going to the code where we have hard-coded, made-up employee and department records and added these records to their respective collections. Let's ensure that the technology department, which has an ID of 3, does not match with a department ID property of any of the employee objects in our employee list collection. We only currently have one employee that is in the technology department according to our data. Let's change the relevant department ID so that there are no employees that are members of the technology department. So let's change this department ID property. Now, no employees are members of the technology department according to our data. Let's run the code. So you can see our technology department record is being returned along with all the other department records in the department list collection, even though its ID property doesn't match the department ID property of any employee records stored in the employee list collection. So simply put, department information for departments that contain employees are included in the query results, and departments that don't contain any employees are also included in the query results. In this example, the technology department is returned even though it contains no matching employee records. So here we have performed a left outer join query using link's group join operator. So let's rewrite this link query using query syntax. You can see here that the group join extension method does not get explicitly called when we implement our query using query syntax. The into keyword is used within the query to create a group of employees for each department. So as discussed, link query syntax does not match exactly when comparing link query syntax to familiar query languages like Transact SQL. But in many ways, it does resemble a language like Transact SQL. In this sense, link query syntax is more intuitive to implement than method syntax when implementing link queries. And just to labor the point, as discussed, it is also better to implement link query syntax for our link queries than implementing method syntax for the same purpose because of better readability. Let's run the code. Great! And we get the exact same result as when we ran the same query that was implemented using method syntax. Now that we have changed the data so that the technology department does not match with any employee records, let's run our join operation that we created earlier. Notice that the results of the join operation doesn't include the technology department. This is because the join operation performs an inner join, and with the group join operation, we are able to perform a left outer join operation. So let's comment out our join query and uncomment our group join query. And for good measure, let's run the code again. And as you can see, the technology department is now included in the results displayed to the screen, even though the technology department does not have any matching employee records. Great! So the left outer join operation returns all records from the outer left collection in the query, but does not return records from the inner collection, where the inner collection records do not match any of the outer collection records. So if there were employee records in the employee list collection that did not match any of the department records in the department list collection, these employees would not appear in the results outputted to the screen. We can prove this. Let's change the department ID of this employee record where the first name property is Bob and the last name property is Jones. We have changed the department ID property for this record to 6, and there is no matching department record, i.e. no department record has an ID of 6. Let's run the code. And you can see that the employee record with first name Bob and last name Jones does not appear within the results. However, even though the Human Resources Department has no matching employee records, it is still included in the results outputted to the screen. Great! Let's add Bob Jones back into the Human Resources Department like this. And let's run the code. Excellent! So hopefully this made it clear how we are able, through link, to use the join operator to perform inner join queries between two object collections, and how we are also able to perform left outer join queries using the group join operator. Hi, and welcome to the third part of a video series on the link technology using C#. This video is also part of the 7th tutorial in an advanced C# course. Link was introduced with C# version 3, which was released on the 19th of November 2007. Link stands for Language Integrated Query. In this video, we are going to focus on code examples that make use of several link operators. The code examples demonstrated in this video will hopefully help us gain an understanding of a broad array of operators that are made available to us through Link. We'll learn how we can use these operators to query and transform data. This quote from the Microsoft Docs provides a basic definition of standard query operators and can be found at this URL. The standard query operators are the methods that form the link pattern. Most of these methods operate on sequences, where a sequence is an object whose type implements the generic IEnumerable interface or the generic IQueryable interface. A lot of the more frequently used query operators have dedicated C# keyword syntax that enables them to be called as part of a query expression. As discussed in the previous video in this video series, it is advantageous to use query syntax rather than method syntax where possible because query syntax is more readable. Note that query expression clauses are translated into calls to query methods at compile time. For a useful tabular representation of standard query operators that have equivalent query expression clauses, please navigate to this URL. We discussed what is meant by deferred execution and immediate execution in the previous part of this video series. For a useful tabular classification of operators in terms of deferred execution or immediate execution, please navigate to this URL. For additional information on deferred execution versus immediate execution and method syntax versus query syntax, please view the second part of this video series. So to gain an understanding of several useful link operators, let's create a few code examples. As with the previous video in this series, I'll be demonstrating these code examples on my Mac platform using Visual Studio for Mac. The code creation process for these code examples is almost exactly the same process as creating the equivalent code examples on a Windows platform using Visual Studio for Windows. The fact that I'm using Visual Studio for Mac should not be a barrier for a learner to follow along with the creation of these code examples. So, let's start by creating a .NET Core Console project. We created a project in the previous video named linkexamples_1. Let's name this project linkexamples_2. In order to save time, let's copy data-related classes that have already been created in the previous videos of this series and incorporate these classes into our new project. These classes contain class definitions for an employee and a department record, as well as code that adds several made-up objects of type employee and department to their respective collections. As in the previous parts of this video series, we can then use these collections of strongly typed objects in our link query examples. So to copy the relevant code, let's navigate to this URL, i.e. to a GitHub repository that was created in the previous video. Let's click on the directory icon labeled linkexamples_1. Then let's click on the file icon labeled program.cs. Let's copy the employee class to our clipboards. And paste the contents of our clipboards within the new project that we have just created. Let's copy the department class to our clipboards and paste the contents of our clipboards below the employee class within our new project. Lastly, let's copy the data class to our clipboards and paste the contents of our clipboards below the department class within our project. So in the previous video, we looked at the following operators: the select projection operator, the where filter operator, the join and group join operators. In this video, we'll create code examples that implement the following operators. We'll start by looking at the following sorting operators: order by, order by descending, then by, and then by descending. We'll then look at these grouping operators, group by and toLOOKUP. We'll then look at these quantifier operators, all, any, and contains. We'll then look at the following filtering operator, of type. Note that another example of a filtering operator is the where operator. We have looked at the where filter operator in the previous parts of this video series. Lastly, we'll look at the following element operators: element at or default, first or default, last or default, single, and single or default. We'll look at even more link operators and create code examples in the next video. The next video will be the final video in this video series on link. Right, let's get started. So let's start by looking at the data-related classes that we copied from GitHub. We have the employee class, which provides a definition for an employee record. We have the department class, which provides a definition for a department record. We have the data class that contains code where lists of hard-coded, made-up employee and department objects are added to their respective collections within their respective methods and returned from their respective methods. In the previous video in this series, we looked at join operators, namely the join operator and the group join operator. So in the context of join operations, the department collection has a one-to-many relationship with the employee records in the employee collection. This simply means that one or many employees can be members of a specific department. A specific employee can be a member of only one department at a point in time. So let's go to our main method. We can use the data.getEmployees method to return a collection of made-up employee records. Let's use this method to assign the relevant collection of employee records to a local variable named employee list. The employee list variable is defined as a generic list that is strongly typed as employee. So here we have red squiggly lines because we need to include a using directive to the system.collections.generic namespace. Let's use the data.getDepartments method to return a collection of made-up department records that have a one-to-many relationship with the relevant collection of employee records, and let's assign the relevant returned collection of department records to a variable named department list. The department list variable is defined as a generic list that is strongly typed as department. So let's get into the creation of our examples. Sorting operators. Order by. So let's create an example for the order by operator. In this example, we want to return all employee records from the employee list collection and order by department ID. To make things a little bit more interesting, let's say we want to include the department name within our outputted results. The problem here is that the department name does not exist in the employee type, so we need to join the employee list collection to the department list collection so that we can include the department name in our results. We can do this by using the join operator. So let's write this query using method syntax so that we can see all the link extension methods used in the relevant query. So we first need to make sure that we include a using directive to the system.link namespace. This directive will give us access to the relevant link operators that we will be implementing in our code examples. We know that the system.link namespace contains two static classes, namely enumerable and queryable, and these static classes mostly contain extension methods. Our link operators, which are implemented in the form of extension methods, are implemented within the enumerable and queryable static classes. So this link query joins the employee list collection to the department list collection on the department ID property of each of the relevant employee records with the ID property of relevant department records. Before we run this query, let's alter the data a bit. Let's make the employee record pertaining to Sarah Jameson a member of the technology department by changing the relevant department ID property from 2 to 3. Let's also change the department for the employee record pertaining to Jane Stevens to the technology department by changing the relevant department ID from 2 to 3. This change to the data will make the effects of our sorting operators more apparent when we view our results. So if we run the query first without the use of any order by operators, note that the data appears to us in the same order as it was added to the employee list. But now let's say there is a requirement to order our results by the department ID property in ascending order. We can do this by chaining the order by extension method to the end of the query, like this. For more information on method chaining, please view the previous video in this series. So we can pass in a lambda expression to the order by extension method to indicate that we wish to order the results by the department ID property. Let's run the code. And you can see that the results are now ordered in ascending order by department ID. If we look at the code that added each department to the department collection, we can see that the Human Resources Department has an ID of 1, the Finance Department has an ID of 2, and the Technology Department has an ID of 3. Our results have been ordered in ascending order based on the department ID property of the employee record. So we can clearly see the effects of the order by operator on our results. Great! If the requirement changed such that we needed to order our results by the department ID property in descending order, we can chain the order by descending extension method instead of the order by extension method for this purpose. Our results are now ordered by department ID in the reverse order when compared to the previous output. Great! So let's say that we want to order our results by the department ID property in ascending order and then by the annual salary property also in ascending order. So let's replace the order by descending extension method with the order by extension method in our results like this. Then let's chain the then by extension method to the query like this. We can then pass a lambda expression to indicate that we wish to further order our results by the annual salary property. The then by extension method will order the results produced by the order by sorting operator in ascending order. Great! And if we want to order by the annual salary property in descending order, we can replace the then by extension method with the then by descending extension method for this purpose. Excellent. We can represent sorting operations within linked queries that are represented using query syntax like this. Note the order by and descending keywords in the query syntax version of the relevant query. We use the order by keyword within our query to order by our first specified property. If we want to subsequently sort on other properties instead of chaining the then by extension method to our query, in query syntax, subsequent properties by which we wish to sort are separated by commas. The descending keyword can follow any of the properties that we wish to sort in descending order. The default order is ascending order. So let's look at the group by and to-lookup grouping operators. Let's start with the group by operator. So this operator is akin to the group by clause we would apply in a transact SQL query. So we can implement the group by operator using the group by extension method, or the group and the by keywords within query syntax to perform the same operation. So let's say we wish to query the employee list collection and group our results by the department ID property. The query using query syntax would look like this. This query is simply grouping our results by the department ID property. Using method syntax, this query would look like this. In all of the link query examples using query syntax that we have looked at up till this point, in this video series, we have ended all our queries with a select operator. Notice that this query does not end with a select operator. It is important to note that a link query implemented in query syntax must either end with a select operator or a grouping operator. Notice how this query does not end with a select operator, but a grouping operation is being performed at the end of this query. So we can traverse the results of this grouping operation using nested for each loops. The outer loop traverses each group that has been created based on the department ID property. The inner loop traverses the item members within each of the groups that have been created in our query based on the department ID property. Great! We could also include the order by operator within our query like this. Let's run the code. Great! We can implement the same query using method syntax using the to-lookup extension method like this. Great! We can also include sorting functionality through the order by operator through the implementation of method chaining like this. Great! Note that the to-lookup method performs the same operation as the group by operator. The only difference is the execution of the group by operation is deferred, whereas the execution of the to-lookup operation is executed immediately. We discussed deferred execution and immediate execution in the previous part of this video series. For more information on deferred execution and immediate execution, please view the second part of this video series. A link to this video has been included below in the description. Note that the results returned from a group by operation and a to-lookup operation return a group contained in a special type of collection that implements an iGrouping generic interface . So let's look at the all, any, and contains quantifier operators. Let's first look at the all and any operators. Let's create a variable named annual salary compare and assign it with a value of 20,000. Let's implement a block of code related to the all operator. Let's implement a similar block of code related to the any operator. So, the all and any operators return a Boolean value. The return value will equal true if the elements in the relevant collection satisfy a condition passed to the relevant method. This condition can be passed in the form of a lambda expression. This query will return true if all employee records have annual salary property values that are greater than 20,000. This query will return true if one or more employee records have an annual salary property value that is greater than 20,000. Let's run the code. Great! This is an expected result. Let's change the annual salary compare variable to 100,000. Great! And let's change the annual salary compare variable to 40,000. So let's move on to the contains operator. So we want to be able to assess whether an employee record exists within our collection of employee records. The contains operator will return true if we pass in an object that is equal in value to an object within the relevant collection. To understand how the contains operator works, let's create an employee record that we know matches an employee record within the employee list collection. Let's copy this record for the employee named Douglas Roberts that is a member of the relevant employee collection. And paste it in our main method. Let's name the variable that stores a reference to the employee record we wish to find within the employee list collection search employee. So how can we assess whether the employee record pertaining to Douglas Roberts exists within the employee list collection? We can use the contains extension method. We can simply pass the variable we named search employee to the contains extension method, which we have invoked on our employee list collection object. So the contains method returns true if the search employee object matches any of the objects within the employee list collection, and false if the search employee object does not match with any of the objects stored within the employee list collection. So let's write code to write an appropriate narrative to the screen based on the Boolean value returned by our query. Let's run the code. And this is not the result we expected because we literally copied and pasted the code representing one of the employee objects that has been added to the employee list collection from our data class to the main method as our search object. So Y is our output indicating that the search employee object does not match any of the objects stored within our employee list collection. This result is unexpected. The answer is that the compiler knows how to compare built-in C# types like, for example, integer or bool. The employee type is a user-defined type or custom type. We need to tell the compiler how we wish to compare two objects of type employee to establish whether two employee objects are equal. So we can do this by creating a class that implements the generic iEquality comparer interface. the iEqualityComparer interface is a member of the system.collections.generic namespace. We have already included a using directive to this namespace within our code. So let's create a class named EmployeeComparer, and let's indicate that we want the EmployeeComparer class to implement the iEqualityComparer generic class that is strongly typed with the employee user-defined type. So let's hover our mouse pointers over the red squiggly line and create the stubs for the methods that we need to implement, like this. So two method stubs have been generated, one named equals and the other named getHashCode. So the getHashCode method is used for the purpose of uniquely identifying an object. We can implement the code for the getHashCode method by returning the hash code of the ID property of the relevant employee object, like this. The equals method must be implemented in a way that establishes how we wish employee objects to be compared when determining whether two employee objects are of equal value. So let's say that we are satisfied with comparing the relevant employee objects based on their ID, first name, and last name properties to establish equality between the relevant employee objects. So we can achieve this with the following code. If the relevant properties are equal, return true, else return false. So we are already passing in the search employee object to the contains method. Let's also pass a newly instantiated object of type EmployeeComparer to an overload version of the contains method, like this. And now we are telling the compiler how we want to compare our employee search object with the objects stored within the employee list collection. Let's run the code. And this is an expected result. The contains method now returns true as expected because our search record matches the employee record for Douglas Roberts within the collection on which we are performing our search. Great. So now let's look at the of-type filter operator. So before we use the of-type filter operator in our code examples, let's create a method named getHeterogeneousDataCollection. Heterogeneous in this context, of course, is referring to the storage of objects of multiple different data types within the same collection. So we can store objects of multiple different data types in an array list. Note that Microsoft does not recommend using array lists for new development. It is far better to use strongly typed lists to store collections of data. For more detail as to why strongly typed lists are recommended, please view a video on generics created by this channel. A link to this video has been included below in the description. So, a use case where we could apply a link query on an array list could be perhaps we have a legacy piece of code that includes an array list containing objects of multiple types, and we need to filter the relevant array list based on specific types. We can achieve this using the of-type link operator. We'll look at how we can do this in a bit. Let's first add some made-up data to an array list. So the array list stores integers, strings, objects of the employee user-defined type, and objects of the department user-defined type. Let's go to our main method and write code to use the of-type operator to query this array list based on specified data types. Let's query for all string values in our array list. Great. So let's query all integer values in our array list. Great. Let's query for all objects of the employee user-defined type. Great. Let's query for all objects of the department user-defined type. Excellent. So you can see how we can query an array list for objects of a specified type using generics and the of-type operator by passing in the relevant type between angle brackets like this. This will return those objects within the array list that are of the specified type. Let's move on to the element operators. Let's look at the element at or default, first or default, last or default, single or default element operators. So let's first look at the element at operator. So the element at operator is used for querying for an item in a collection that resides at a specified ordinal location within the relevant collection. So we can pass an integer value representing the relevant element's location in the relevant collection into the element at method to return the desired item's value from the relevant collection, like this. Great, and our query has returned the value for the relevant element. But what happens if we pass in a value representing a position in the relevant collection where an element does not exist? So let's try this. Let's pass in a value of 8. Right, so it is important to note that no item exists within the relevant collection at ordinal position 8. So in this case, an argument out of range exception is thrown. This brings us to an important point about the difference between the element at and the element at or default method. If we replace the element at method with the element at or default method, and we query the relevant collection for an item at a position where the desired item does not exist within the relevant collection, the element at or default method does not throw an exception, but rather returns the default value for the desired item's relevant data type. Let's briefly discuss what we mean by a default value for a particular data type. The C# language associates default values for C# data types. So if, for example, we are querying a collection of integers using the element at or default method for a value that did not exist at the specified location in the relevant collection, the element at or default method would return the default value for the integer data type, which is a value of 0. The integer value of 0 is the default value for the integer data type in C#. If, however, we are querying a collection containing a reference type object like an object of our user-defined type employee, the default value returned by the element at or default method would be null. Null is the default value for reference type data types like user-defined types or the string data type. For more detail regarding default values in C#, please navigate to this URL. So let's use the element at or default method to query the relevant collection of employees for a value at position 8, i.e. where no employee object is present within the relevant collection. We can then write code to check if the returned value is null. And you can see that an exception is not thrown and no results are outputted to the screen, which is an expected result because the query returned a null value. Let's pass in a value of 2 and then 1. And in both cases, the appropriate result is outputted to the screen. So let's write code to output an appropriate narrative to the user based on the value returned from the element at or default method. So let's pass in a value of 12. The output indicating that the return value is null, i.e., the employee object does not exist in the collection, is outputted to the screen. This is an expected result. Great. So the first operator returns the first element in a collection if no condition is specified. We have the option of passing a condition to the first method, or we can leave the brackets following the first method empty. If we do not specify a condition, the query will return the first element in the relevant collection. If a condition is specified, the first operator will return the first element in the collection that satisfies the specified condition. We can specify a condition in the form of a lambda expression. Right, to prove this, let's first create a strongly typed list of integer values. So if we query this collection using the first operator and don't provide a condition passed as an argument to the first method, the query returns the first item in the collection as expected. So let's pass a condition in the form of a lambda expression to the first extension method. So this condition is simply querying the collection for the first even number in the collection. Let's run the code. Great. But now what happens if we alter the collection of values so that no value satisfies the condition, i.e. no even numbers exist within the relevant collection? An invalid operation exception is thrown. So if we don't want an exception to be thrown, we can replace the first operator with the first or default operator. As you may have guessed, where no items in the relevant collection satisfy the relevant condition, this method will not throw an exception, but will rather return the default value of the relevant data type. We know that the default value for the integer data type is 0. Let's write code to output an appropriate narrative to the screen if the relevant condition is not satisfied. Let's run the code. And this is an expected result. So let's include an element in the relevant list that does satisfy the condition. Excellent. So the last or default operators work in much the same way as the first or default operators. The only difference is that the last item in the collection is returned where no condition is specified. The last item that satisfies a specified condition in the collection is returned when a condition is specified. The last method will throw an exception if an appropriate element is not present within the relevant list. We can use the last or default method rather than the last method to return the default value for the relevant data type in the case where an appropriate element in the relevant collection is not present. Great! So let's move on to the single and single or default element operators. The single operator returns the only element in a collection or one element that satisfies a specified condition from a collection. We have the option of passing a condition into the single method through the use of a method overload, or we can leave the brackets following the single method empty, which means we have chosen not to pass in a condition into the single method. If we choose not to pass in a condition into the single method, and there's more than one element or zero elements in the collection, an invalid operation exception will be thrown. If, however, there's only a single element in the collection, the value for this element will be returned by the query. If we do choose to pass in a condition and zero or more than one element satisfies the condition, an invalid operation exception will be thrown. If we pass in a condition to the single method and only a single element satisfies the condition, the value for this single element will be returned from the relevant single operation. Let's apply the single operator to a collection of employees. Let's first modify the data for our list of employees so that only one employee element exists within the relevant employee collection. Let's write code using the single operator to query the relevant employee list. Great! This is an expected result. Let's now include the employees that we just commented out back within the relevant employee list. Let's run the code. And an invalid operation exception is thrown as expected. This is because more than one employee resides in the list. If there is only one item in the relevant collection, the value for this item is returned. If there are 0 items or more than one item in the collection, and a condition is not specified for the single operator, an invalid operation exception is thrown. So let's test the single method, and this time specify a condition where one item within the relevant collection satisfies the specified condition. Great! Let's specify a condition where more than one item in the relevant collection satisfies the specified condition. As you can see, an invalid operation exception is thrown. So let's test the same scenario, i.e., more than one element in the relevant collection satisfies the specified condition, but this time let's use the single or default method. That's interesting. So note, where more than one element satisfies the specified condition when the single or default method is applied in the relevant query, an invalid operation exception is thrown, just like when the single method is applied to perform the same operation. So we can use the single or default method instead of the single method if we don't want an exception to be thrown under the scenario where no elements exist within the collection. The default value for the data type will instead be returned by the query. If a condition is specified for the single or default method, and no elements satisfy the condition, the same result will be produced, i.e., the default value for the data type of the element stored in the collection will be returned by the query. If a single item is present within the relevant collection, and the single or default method is applied to perform a query against the relevant collection, the single element's value that exists within the relevant collection will be returned by the query. Hi and welcome to the fourth and final part in this video series on the link technology using C#. This video is also part of the 7th tutorial in an advanced C# course. This video is a continuation of the previous 3 videos in this video series on link, so I recommend viewing the previous 3 videos in this video series before viewing this video. In the previous video in this series, we looked at code examples where certain link operators were implemented to query and transform data. This video is a continuation of the previous video in this series, where we'll create code examples using some of the other link operators to gain a broader understanding of what can be accomplished using the link technology in C#. So in the previous videos in this series, we have created code examples using the following link operators. The sorting operators, order by descending, and then by descending. The grouping operators, group by and to lookup. The quantifier operators, all, any, and contains. The filter operators, of type and where. The element operators, element at or default, first or default, last or default, single and single or default. The join operators, join and group join. We have already looked at the select projection operator, and we'll also look at the select operator in this video, and in addition to this, we'll also look at the select many projection operator. So in this video, we'll look at the following link operators. The equality operator, sequence equal. The concatenation operator, concat. The set operators, distinct, except, intersect, and union. The generation operators, default if empty, empty, range, and repeat operators. The aggregate operators, aggregate, average, count, sum, and max. The partitioning operators, skip while, take, and take while. The conversion operators, to list, to dictionary, and to array. And lastly, the projection operators, select and select many. We'll also look at the following keywords that are useful when used in queries implemented in query syntax, namely the let and into keywords. We have looked at the select projection operator already in previous videos, but we'll look at this operator again in this video, as well as look at the select many projection operator. We'll then be able to gain an understanding of the difference between the select and the select many projection operators. As in the previous videos, I'll be demonstrating the code examples on my Mac platform. If you are using a Windows platform to follow along, the experience of creating these code examples will be almost exactly the same. So the fact that I'm using Visual Studio for Mac should not be a barrier for a learner using Visual Studio for Windows to follow along with the creation of these code examples. Okay, so let's create a .NET Core console project. So the official release of .NET 5 has now been released. So I'll be running this project using the new .NET 5 .NET runtime. For more information on the significance of the .NET 5 runtime, please view the second part of this advanced C# course. I've included a link to this video below in the description. The project we created in the last video was named linkexamples_2. Let's name this project linkexamples_3. So as we did in the previous video, let's navigate to this URL where we can access code on GitHub for the project that was created in the previous video of this series. Here we can copy the data-related code that we created in our previous project so that we can reuse these data-related classes in this project. Let's click the directory icon labeled link examples_2. Let's then click the file icon labeled program.cs. Let's copy the class named employee and paste the contents of our clipboards to our new project. Let's do the same for the department class. And the data class. Okay, so we won't be using the getHeterogeneousDataCollection method that resides in the data class in this video, so let's delete this method. Let's refresh our memories about the classes we have just copied and pasted from GitHub. The employee class contains a definition for an employee record. The department class contains a definition for a department record. The data class contains hard-coded, made-up data for employee records and department records. The employee records are stored in a generic list strongly typed as employee. The department records are stored in a generic list that is strongly typed as department. We can access the data stored in the employee list collection from calling client code, in this case, this will be the main method, by calling the static method named getEmployees. We can access the data stored in the department list collection by calling the static method named getDepartments. Note that the data class in which these methods reside is a static class. Let's navigate to the main method, and before we create our example code, let's add the appropriate using directives. First, let's add a using directive to the system.collections.generic namespace. The generic list type is a member of this namespace. Let's also add a using directive to the system.link namespace. Once we have added our system.link using directive, we can access our link operators on collection types that implement the IEnumerable interface. So, for example, list types implement the IEnumerable generic interface. So we are able to access extension methods stored within the enumerable static class, which is a member of the system.link namespace, by including a using directive to the system.link namespace. The queryable static class also includes link extension methods and is a member of the system.link namespace. For more information on how extension methods work in C#, please view the first video in this video series. A link to this video has been included below in the description. Before we get started creating our code examples, I want to draw your attention to what might be an issue for Visual Studio for Mac users. When we run our code interactively through Visual Studio for Mac, by default, the output may appear in the terminal console window within Visual Studio for Mac, like this. This is absolutely fine for testing code, but you may prefer to present the output externally, i.e. in a terminal console window outside of Visual Studio for Mac. If you would prefer to present your output externally, i.e. outside of Visual Studio for Mac, please navigate to Visual Studio for Mac Preferences, then under the heading marked Other, select the item labeled Terminal. In the right pane of the relevant dialog box, ensure that the Enable Integrated Terminal checkbox is unchecked. This is obviously not a functional issue, it really comes down to personal preference. Let's define a generic list variable named employee list that is strongly typed as employee, and let's assign the collection of employee records returned by the data.getEmployees static method to the employee list variable. Let's define a generic list variable named department list that is strongly typed as department, and let's assign the collection of department records returned by the data.getDepartment static method to the department list variable. Okay, so we are now ready to query and transform data using LINQ. So let's start with the equality operator, sequence equal. So the use case here is we want to compare two lists of data, and we want to know if these two lists contain elements of equal value and each element in each of the relevant lists are stored in the same order. If each item in each list matches in terms of value and order, the sequence equal method will return true. If any of the items in each of the relevant lists does not match in terms of value and order, the sequence equal method returns false. Let's create a generic list named integer list1 that is strongly typed as integer. Let's copy and paste this line of code to the next line. Let's change the name of the second list to integer list 2. Let's run the code. And the sequence equal method returns true, because the values and sequence of elements in integer list 1 is identical to the values and sequence of elements in integer list 2. Let's change the order of the items in integer list 2, so this sequence of values is not equal to the sequence of values stored in the list named integer list 1. Let's run the code, and this is an expected result. Let's change integer list 2 once again for good measure. And this is an expected result. Great. So let's change the data in integer list 2 so that the order and values in the lists are equal. And now the result is true, which is an expected result. That was pretty straightforward, i.e., comparing two sequences of values of a primitive data type, i.e. the integer data type. But what if we want to test this type of equality between two lists that are strongly typed with a complex type, like for example our employee user defined type? So let's define a variable named employee list compare as a generic list type that is strongly typed as employee, and let's assign the collection returned from the data.getEmployees static method to our employee list compare variable. Let's run a sequence equal operation and compare the values stored within our employee list compare collection with the values stored within the employee list collection. So one would expect the result of this sequence equal operation to return true because both collections contain exactly the same data. Let's see what happens. Oh, and false is returned. The reason why false is returned is because we need to tell the compiler how to establish equality between objects of the relevant complex type, i.e. in this case, the employee type. So we achieved this in the previous video in this series by implementing the built-in iEquality comparer generic interface. So let's copy the relevant code for this that we implemented in the previous video in this series. Let's navigate to the GitHub repository at this URL that contains the code we created in the previous video in this series. Let's copy the class named employee comparer to our clipboards and paste the contents of our clipboards to our projects like this. We have red squiggly lines, so let's fix this by bringing in the appropriate using directive. So here we have implemented a class named employee comparer that implements the generic iEquality comparer interface that is strongly typed as employee. This gives us a way of telling the compiler how we want objects in our lists of type employee to be compared when determining equality between the relevant objects. So we are explicitly doing this here in the equals method, where we are comparing the ID, first name, and last name properties between two employee objects. We are returning true if the relevant properties of the relevant two objects are equal, and false is returned if any of the relevant properties of our two objects are not equal. Within the getHashCode method, we are returning the hash code of the ID property of the relevant employee objects. For more information on hash codes, please navigate to this URL. So now let's go to our main method, and we can pass in a new instance of the employee comparer class to an overloaded version of the sequence equal method. This object will tell the compiler explicitly how we want our employee objects to be compared. Let's run the code. And now the sequence equal operator works as expected. So note that we need to tell the compiler how we want objects that are defined as complex types to be compared when determining equality between the relevant objects. We can do this by creating a class that appropriately implements the I-equality comparer generic interface. Great! Let's move on to the concatenation operator named concat. We can use the concat operator to append one collection of data to another collection of data. So let's see the concat operator in action. Let's create a collection of integer values. Let's then create another collection of integer values. Let's append the second collection of integer values with the first collection of integer values using the concat operator. Let's write code to output the results of this concatenation operation to the screen. Let's run the code. Great! Let's do another example, but this time let's append a collection that contains a collection of objects of a complex type to another collection of objects of the same complex type. The complex type we'll use in this example will be our employee user-defined type. Once again, we can use the concat operator to achieve what we want here. Let's run the code. Great! Let's move on to the aggregate operators. Let's first look at the aggregate operator. Using the aggregate operator, we can perform a custom operation on values within a collection. Let's say we have a requirement where we need to provide a total for the annual salaries of our employee records. We also need to include the addition of an appropriate annual salary bonus in the final result. Let's say a manager gets a bonus of 4% and employees that aren't managers get a bonus of 2%. So let's say we have a use case where we need a result that is a total of all employee annual salaries, which must include each employee's bonus. We can take this added complexity into account when totaling up our employee annual salaries through the use of the aggregate operator. So the first argument is the seed value. So let's provide 0 for this argument. Using this argument, we are initializing the value that will be returned by our aggregate operator. The next argument is of a delegate type, where we can include the logic for our aggregation functionality in the form of a lambda expression. So as you can see in our logic for the relevant lambda expression argument, we are checking to see if the relevant employee is a manager, whereby we need to add a bonus of 4% to the relevant employee's annual salary. If the employee is not a manager, we need to add a bonus of 2% to the relevant employee's annual salary. We can then include the appropriate bonus amount in our calculation. So we are adding up all employee annual salaries, which includes each employee's appropriate bonus. Let's run the code. Great! Say we want to output a comma-delimited string from our employee list collection. Each delimited item containing the employee full name, a dash, then the employee annual salary. Each annual salary must include the appropriate bonus. We also want to include a label preceding the comma-delimited string. We can achieve this using the aggregate operator like this. The first argument is the label, where an appropriate value could be something like employee annual salaries including bonus. Then the logic of our aggregation functionality can be expressed in a lambda expression for the second argument, like this. We can apply the same logic to include appropriate bonuses from our previous example. Let's run the code. Great, but we have a slight issue where a comma is presented at the end of our string. We don't want this comma in our final result. We can express this by passing a lambda expression as our third argument to an overloaded version of the aggregate operator. This argument allows us to perform a final operation on the results produced by the lambda expression passed in as the second argument. We first need to include another datatype argument with an angle brackets following the aggregate method to declare the datatype of the final output, i.e. provided by the lambda expression we are passing in to the last parameter of this overloaded version of the aggregate method. In the lambda expression passed in as our final argument, we are using the substring method to remove two characters from the end of the result, which means a comma and a space will be removed. This result is what we want. Excellent. So let's move on to the average aggregate operator. So to find the average annual salary for a list of employees, we can apply this code. Great. If we want to find the average salary for all employees in the technology department, we can use method chaining and the where operator to achieve this, like this. Great. For more information on method chaining, please view the second part of this video series. Let's move on to the count aggregate operator. So if we want to know how many employee records we have in our collection of employee records, we can apply the count operator like this. Great. If we want to know how many employees are members of the technology department, we can pass in a condition as an argument to the count operator. The condition that is passed in as an argument to the count method can be expressed in the form of a lambda expression. Great. Let's move on to the sum aggregate operator. So let's keep this simple. We just want the sum total of all annual salaries of all employee records stored in our employee list collection. We can apply the sum operator to achieve this. Great. Let's move on to the max aggregate operator. So if we want to return the highest annual salary property of all employee records stored in our employee list collection, we can apply the max aggregate operator in a link query like this. Great! Let's move on to the generation operators, namely default if empty, empty, range, and repeat. Let's first look at the default if empty operator. So we can use the default if empty operator to return a new IEnumerable collection that when, for example, we apply the element at method on the new collection to check if the new collection is empty, the operation will return the default value for the relevant type used to strongly type the relevant collection. A query using, for example, the element at method against a collection returned from a default if empty operation will not throw an exception if the collection is empty. The default value of the type with which the relevant collection is strongly typed will instead be returned. For more information on default values for C# data types, please navigate to this URL. We'll see later how we can pass in a value to the default if empty method to specify our own default value that we'd prefer to be returned when, for example, the element at method is used to check if the relevant collection is empty, rather than the default C# value for the relevant data type. Let's look at an example using the default if empty method. So let's create an empty list of integer values. Let's perform a default if empty operation on this collection of integer values and assign the returned collection to a new collection of integer values. Let's use the element at operator and pass in 0 to the element at method to check if the collection is empty. you can see that the element at operator returns the default value for the integer data type, which is 0. This is an expected result. Let's create another example, but this time let's use the employee data type to strongly type our collections. As discussed, the default value for a reference type in C# is null. But as discussed, we can pass in a default value that we would prefer to be returned by, for example, the element at operator when the relevant collection is empty. So let's pass in an employee object where the ID property of the relevant employee object is set to 0. Null is not returned, as would be the case if we hadn't passed in a value to the default ifEmpty method, because we have specified our own default value where the ID property of the default employee object is 0. Great. Similarly, we could have set the default value for our integer collection example by, for example, passing in 999999 to the default ifEmpty method. Instead of returning the default C# value for an integer, which is 0, 999999 is returned. This is an expected result. Excellent. Right, let's look at the empty method. So we can use the empty method to generate a new empty collection. So for example, we want to create a new IEnumerable generic collection of employee records. We can do this by using the empty operator like this. Note, the empty method is not an extension method of IEnumerable or IQueryable like other LINQ methods. It is a static method included in the enumerable static class. So for example, we could instantiate a new empty generic list strongly typed with the employee user-defined type through the use of the empty method. We can then chain the toList conversion operator to this operation and return an empty generic list. We are using the toList operator to convert an IEnumerable generic collection that is strongly typed with the employee data type to a generic list that is strongly typed as employee. So for good measure, let's add a new employee item to our new list that we have generated through the use of the empty method and the use of the toList conversion operator. Let's write code to write the items, or in this case one item, stored in our new list to the screen. Great. Right, let's move on to the range generation operator. We can use the range operator to return a collection of values that are within a specified range. So let's clarify this with an example. We want to return a range of integer values in a collection where the first item in the range has a value of 25 and each subsequent item is incremented by a value of 1 until there are a total of 20 values in the relevant collection. We can achieve this by using the range method like this. In this example, the first argument specified is 25. This is the value of the first element, and the second argument specifies the number of elements to include in the relevant generated collection. When each item is added to the collection, it is incremented by a value of 1. So the second item will be 26, the third item will be 27, the fourth item will be 28, and so on. Let's run the code. Great. So using the range operator, we have generated a collection of integer values that fall within a specified range. Excellent. Let's say we want to generate a collection of a specified amount of elements where a value for each element in the collection is repeated. We can use the repeat operator for this purpose, like this. Great. Let's move on to the set operators, namely distinct, except, intersect, and union. Let's start with distinct. So let's say we have a strongly typed generic list that contains a list of integer values, some of which are repeating values. We want to perform a query against this list of integer values where we only want distinct values returned. We can achieve this by applying the distinct operator to our query like this. Great! Let's say that we have two collections of a specific type and we want to return elements with values in our first collection that are not equal to any of the values of the elements in our second collection. We can achieve this by using the except operator. Let's look at an example of using the except operator applied to two collections of integer values. So 1 and 2 are returned in our results collection because these values exist in our first collection and don't exist in the second collection. The values 3 and 4 exist in our first collection and also exist in our second collection. The values 5 and 6 exist in our second collection, and even though these items don't exist in our first collection, the except operator does not return these items as part of the results collection, because in this example, the except operator returns values that exist in the first collection and don't exist in the second collection. Let's try an example using complex types. Let's use our employee type. Let's create a generic list strongly typed as employee. Let's copy data that we know will exist within our employee list collection and add these items to the list we have named employee list 2. Let's add some additional items to the employee list 2 collection. Let's then call the except method on the employee list collection and pass in the employee list 2 collection as an argument to the except method. Then let's assign the results of this operation to an implicitly typed variable named results. We have of course used the var keyword to implicitly type our results variable. Let's write code to traverse the results and output the results to the screen. Let's run the code and see what happens. And this result is not expected. The output contains all items within the employee list collection. I would have expected that the items that were copied from the data class and added to the employee list 2 collection, as well as the other items that we added to the employee list collection, would be excluded from the results. The reason for the unexpected results is because we have not told the compiler how to compare employee objects when determining if one employee object is equal to another employee object. So how can we let the compiler know how we want one employee to be compared to another employee within our collections when determining equality between the two relevant objects? You may have guessed already how we can achieve this. We first need to create a class that implements the iEquality comparer generic interface. We can then write code to establish how one employee object should be compared to another employee object when determining equality between the relevant objects. We have already included the code for this, which we applied when we created code to perform a sequence equal operation on two lists that were strongly typed as employee. So we have our class named employee comparer that implements the iEquality comparer generic interface. So we can reuse this class for our example that performs an accept operation on two generic lists that are strongly typed as employee. So all we need to do is create a new object of type employee comparer and pass this object into an overloaded version of the accept method like this. Let's run the code. Great! This is now an expected result. Let's move on to the intersect operator. So we can use the intersect set operator to return a collection containing only those items that exist in the employee list collection that are equal to the items that exist within the employee list 2 collection. And now that we know we are comparing elements in two collections that are strongly typed with the employee complex type, we need to pass in a new object of the employee comparer type, i.e. a type that appropriately implements the generic I-equality comparer interface. This tells the compiler how to compare two objects of type employee when determining if the relevant employee objects are equal. Let's run the code. And this is an expected result. Great. Let's move on to the union operator. The union extension method requires two collections and returns a new collection that includes distinct elements from both the collections. We can again use the same data we have used in the previous two examples to test the union operator. Right, let's write the code for this. You will notice we are also passing in an object of type employee comparer to the union method. Let's test the code. Great! So let's see what happens in this example when we don't pass in an object of type employee comparer to the union method. You can see that duplicate records are included in the results as a consequence of not passing in an object derived from a class that appropriately implements the generic I-equality comparer interface. And of course, we know we have already created such a class. So let's ensure that we pass in our object of type employee comparer to the union method so that only distinct employee objects are included within our results. Excellent. So let's move on to the partitioning operators. These partitioning operators include the skip, skip while, take, and take while operators. Let's first look at the skip operator. Use the skip operator to skip over a given number of elements in a sequence and then return the remainder. So let's query our employee list collection using the skip operator. Let's skip over 2 of the elements stored in our employee list collection and return the remainder of the elements using the skip operator. Great, this is an expected result. Let's look at the skip while operator. Using the skip while operator bypasses elements in a sequence as long as a specified condition is true, and then returns the remaining elements. Let's see this operator in action. So the condition here is skip elements in our sequence of employee objects in the employee list collection while the relevant employee object's annual salaries are above 50,000. Great, this is an expected result. Just to make things a little bit more clear on how this operator works, let's add a new employee record to the employee list collection. This employee record has an annual salary of 100,000, which of course is above 50,000. Let's run the code. And you can see that while the condition is true, the items in the relevant collection are skipped, i.e. will not be returned from the query. However, all subsequent elements in the sequence will be returned once the condition returns false. Even though the last element in the relevant sequence has an annual salary property greater than 50,000, it is still returned, because the third element in the sequence caused the condition to return false. The fact that the last element has an annual salary above 50,000 and therefore causes the condition to be true doesn't mean that the last item will be returned by our query. Note that once the condition returns false, all items from that point will be returned from our query. Right, let's move on to the take partition operator. The take operator is used to return a specified number of contiguous elements from the start of a sequence. Let's see this operator in action. This is an expected result. Great! The first two elements in the relevant sequence of elements in our employee list collection are returned by our query. So let's move on to the take while partitioning operator. The take while operator returns elements from a sequence as long as a specified condition is true, and then skips the remaining elements. So let's use the same condition that we used in the skip while operator example. So here we are using the take while operator to return elements from the relevant sequence that have an annual salary above 50,000. So the first two elements in the sequence are returned by our query. As soon as the third element is evaluated and the condition returns false, the elements from that point onwards in the relevant sequence will not be returned by our query. So for example, the fact that the fifth element in the employee list collection has an annual salary property that is greater than 50,000 is irrelevant, because when the third element causes the condition to return false, and in terms of the take while operator this means that from that point onwards, the rest of the elements in the relevant sequence will not be returned by our query. Great! Let's look at the conversion operators toList, toDictionary, and toArray. So let's look at the toList conversion operator. A query written in query syntax will return an IEnumerable collection containing the results of the query. What if we need our results to be returned as a generic list? We can achieve this using the toList conversion operator. Let's create an example to clarify this point. So for this example, let's query our employee list collection for employee records that have an annual salary property greater than 50,000 using query syntax. Note the red squiggly lines here. This is because we are attempting to assign an IEnumerable collection to a variable of type generic list. The compiler is telling us that we have created a type mismatch. So we can use the toList operator to convert the IEnumerable collection returned by our query to a generic list by wrapping the relevant query in brackets, adding a dot after the last bracket, and applying the toList operator like this. So now you can see the red squiggly lines disappear because we have removed the type mismatch. Let's run the code. Excellent. As discussed earlier in this video series, wherever a to conversion operator is applied to a query, as we have done here, this causes the query to execute immediately, i.e., query execution is not deferred, it is executed immediately. So if we want to convert an IEnumerable collection returned from a query to a dictionary object, we can apply the toDictionary operator to the query. Let's create an example to clarify what is meant by this. So, as in the previous example, here we have a standard query written in query syntax to query our employee list collection for all elements where the relevant elements have annual salary properties that have values greater than 50,000. So this is a basic query that will return an IEnumerable collection. But what if we want to return a collection where each element has a unique key associated with the relevant element? We can do this by converting the query result to a dictionary generic collection type. So let's alter our code so that the IEnumerable collection returned by our query is converted into a generic dictionary collection. So within angle brackets after toDictionary, we need to pass in two data types. The first data type declares the data type of the value stored in the dictionary. The second data type declares the data type of the key that will be used to uniquely identify each element in the collection. So the first data type is of type employee, and the second data type is of type int. Note that we want each element to be keyed on the employee ID property. We can express this by passing in an appropriate lambda expression to the toDictionary method like this. So let's traverse the key values stored in our dictionary object using a for each loop. Note how we are able to use the key values to retrieve the values of each element stored in the dictionary. We are doing this by passing in the relevant key within square brackets to the dictionary object. Here we are outputting the key as well as each employee's first name and last name to the screen. And as you can see, we have each employee's ID, which we have designated as our key value, followed by the corresponding employee's first name and last name properties. Excellent. We have successfully converted a query result from an IEnumerable collection to a dictionary object. As discussed, when we call any of the two conversion operators on a query result, this causes our query to execute immediately. For more information on deferred execution versus immediate execution, please view the second part of this video series. For good measure, let's also create a result using the toArray conversion method. So if we try to assign the results of this query to a variable defined as an array of employees, the compiler complains of a type mismatch. The query result is returned as an IEnumerable collection and not an array of employee objects. To remove the type mismatch, we can apply the toArray method like this. Great. So let's discuss the let and the into clauses that can be applied when using query syntax to represent a LINQ query. Let's look at the Microsoft Docs for an overview of the let clause. This overview of the let clause can be found at this URL. In a query expression, it is sometimes useful to store the result of a sub-expression in order to use it in subsequent clauses. You can do this with the let keyword, which creates a new range variable and initializes it with the result of the expression you supply. Once initialized with a value, the range variable cannot be used to store another value. However, if the range variable holds a queryable type, it can be queried. So let's look at a basic example using the let keyword in a LINQ query. Let's say we wish to query our employees based on employee initials. Now we don't have an initials property for an employee record, but within our query, using the let keyword, we can extract the initials from each employee record's first name and last name properties and assign the result of this extraction process to a variable named initials, directly within our query using the let keyword. This allows us to use the initials variable in our where clause as well as reuse the initials variable within our select clause. Through the use of the let clause, we can also apply a condition, and based on the evaluation of that condition, store a value in a variable that can be used later in the query, like for example within a where clause. Here we have a condition where we need to add an appropriate bonus to the annual salary property, based on whether the employee is a manager or not a manager. If the employee is a manager, we need to add a bonus of 4% to the relevant employee record's annual salary property. If the employee is not a manager, we need to add a bonus of 2% to the relevant employee record's annual salary property. We can store the relevant annual salary plus bonus value for each employee record by assigning the value returned by a ternary operator to a variable. We have named this variable annual salary plus bonus. The let clause in this example enables us to reuse the annual salary plus bonus variable, both within the where clause and the select clause later in the query. Let's run the code. Excellent. Let's look at the into keyword. We can use the into keyword in a link query to collate data within a group, and then after this operation, we are able to perform a filter operation within the same query, if required, on the grouped data through the use of a where clause. So for example, let's use a link query to first create a group of high-earning employees based on a condition. Let's say that the employee must earn above $50,000 to fit into the relevant group. We can use the where clause at this point in the query to appropriately filter the relevant employee records and the into keyword to put the filtered data into the relevant group of high-earning employees. So we can use the into keyword to group the high-earning employees into a group named high earners. Let's say we then want to further filter this group of high-earning employees by management status. So we only want these employee records where the isManager property is set to true returned from our query. We want to know which of those high-earning employees are managers. So we can use another where clause within our query to filter the high earner group based on the relevant condition. We have used a where clause earlier in our query to create the group of high earning employees. Then once the group is created through the use of the into keyword, we can further filter the group of high earning employees based on each employee record's isManager property. So we are able to include another where clause in our query to filter the grouped data. Let's run the code. Great. So lastly, let's look at the select and the select many projection operators. In this video series, we have already looked at the select projection operator. So the focus in this example is on the select many operator. We want to know how it differs from the select operator and in what circumstances we may wish to apply the select many operator in a link query. Let's navigate to a Microsoft Docs webpage to see what the Microsoft Docs say about these two projection operators. Projection refers to the operation of transforming an object into a new form that often consists only of those properties that will be subsequently used. By using projection, we can construct a new type that is built from each object. You can project a property and perform a mathematical function on it. You can also project the original object without changing it. Select projects values that are based on a transform function. Select many projects sequences of values that are based on a transform function and then flattens them into one sequence. To understand the difference between the select many operator and the select operator, let's modify our department class so that it includes a property that stores a collection of employees. We have already discussed that department records have a one-to-many relationship with employee records. So each department object will now store a collection of related employee records. Let's also alter the getDepartments static method that resides in the data static class so that the getDepartments static method accepts an argument containing a collection of employee objects. Then for each department object added to the department list collection within the getDepartment static method, let's include a query to return an appropriate collection of employees, i.e. those employee records that have a department ID property matching the ID property of the relevant department object. So let's go to the main method and pass in the collection of employees to the getDepartment method. So now the getDepartments method will return a collection where each department contains a related collection of employee records. So now, what if we want to query the department list collection for all employees? We can achieve this using the select operator, but when traversing the results of the select operation, we will need to use an outer and an inner for each loop, like this. In this scenario, the select many operator is better to use for this purpose. The select many operator is better in this case because we can use one for each loop to traverse the results of our query, unlike where we needed to use an additional nested for each loop to traverse the results of our query, where we used the select operator. Behind the scenes, as it were, the select many operator appropriately flattens the results. And this means we don't need to use a nested for each loop to traverse the results of our query. We are able to use one for each loop for this purpose. Excellent. So we have covered a lot of ground in this video series on link operators. I would encourage you to practice using these operators to become proficient in writing link queries. This is a very powerful technology and is used with Entity Framework to perform database queries in modern .NET applications. Entity Framework is now the recommended technology to use in .NET for implementing database-related functionality in .NET applications. If we navigate to this Microsoft Docs webpage, we can see this paragraph that states, Entity Framework Core is a modern, object-based mapper for .NET. It supports link queries, change tracking, updates, and schema migrations. EF Core works with many databases, including SQL Database, on-premises and Azure, SQLite, MySQL, Postgres, and Azure Cosmos DB. This makes Link a very important technology to learn for .NET developers. Link enables developers to write one set of code that can be applied to handle data-related functionality for multiple different data sources. In Link, expression trees are used to represent structured queries that target sources of data that implement the generic iQueryable interface. If you would like to delve deeper into expression trees, please navigate to this URL. So let's summarize what we have learned in our 4-part series on using the link technology in C#. In the first part of this video series, we created our own extension method to filter data. We also demonstrated how a lambda expression can be used to express a condition that can be passed into our extension method to filter the data and return the filtered results from a query. The reason we created the filter extension method is because Link is mostly made up of extension methods stored in 2 static classes, namely a static class named enumerable and a static class named queryable. We are able to access the extension methods within these static classes by including a using directive to the system.link namespace. The enumerable and queryable classes are both members of the system.link namespace. In the second part of this series, we demonstrated examples using the select, where, join, and group join operators. We also discussed the difference between when a query is executed with deferred execution or immediate execution. We discussed how a link query is executed with deferred execution but we can make the link query execute immediately by applying a to conversion operator to the query. For example, to list, to dictionary, or to array. In the third video in this series, we demonstrated code examples using the following link operators. Sorting operators: order by descending, and then by descending. Grouping operators: group by and to lookup. Quantifier operators: all, any, and contains. Filter operators: of type and where. Element operators: element at or default, first or default, last or default, single, and single or default. In the fourth and final video in this series, we demonstrated code examples using the following link operators. The equality operator, sequence equal. The concatenation operator, concat. The set operators, distinct, except, intersect, and union. The generation operators, default if empty, empty, range, and repeat operators. The aggregate operators, aggregate, average, count, sum, and max. The partitioning operators, skip, skip while, take, and take while. The conversion operators, to list, to dictionary, and to array. Projection operators, select, and select many. In this video, we also looked at code examples using the let and the into keywords. I hope you have enjoyed this video series on using the link technology in C#. Hi and welcome to the 8th part of this advanced C# course. In this video, we'll focus on the use of attributes in C#. For more content on advanced C# concepts and much more, please consider subscribing and please ring the bell so that you'll be notified of future content. If you like this video at any point, please consider giving it a thumbs up. It will be greatly appreciated. So, let's discuss attributes. Attributes allow the developer to add metadata in a declarative way to program elements in code, for example, classes, methods, properties, parameters, etc. A declared attribute is instantiated into an object at runtime, and at compile time, we can declare attributes against program elements to provide additional metadata to relevant program elements. The developer is also able to declare global attributes against assemblies, and in doing so add or modify metadata about the relevant assembly. So, the developer can use attributes to add or modify metadata about a particular program element or the assembly itself. In this video, we'll also briefly look at reflection. Reflection is a technology that we can use to read the metadata provided through the use of attributes at runtime. We are then able to, for example, implement code logic based on the metadata provided through the use of attributes. We'll look at how we can do this later in this video. There are two broad categories for attributes: predefined attributes and custom attributes. Predefined attributes are built into the base class libraries in .NET. In this video, we'll look at two main types of predefined attributes: global predefined attributes and general predefined attributes. Global attributes, like for example assembly version attribute and assembly description attribute, facilitate adding and modifying metadata for an assembly. General attributes, like for example conditional attribute, obsolete attribute, and attribute usage, can be applied to appropriate program elements. We'll start by implementing a code example using the assembly version attribute and assembly description attribute, which are global attributes. We'll use reflection to read the relevant assembly metadata and output the assembly metadata to the console screen. We'll then implement a code example using the following general attributes: conditional attribute, obsolete attribute, and attribute usage. The attribute usage attribute will be declared on our own custom attributes that we'll create a bit later in this video. We'll use custom attributes and reflection to implement field validation functionality. We'll demonstrate how custom attributes can be created by creating classes that inherit from the built-in system.attribute class. Later in this video, we are going to create custom attributes as part of validation logic that imitates how the ASP.NET MVC framework provides flexibility to developers through the use of reusable validation-related attributes. This video sets us up well for the next video provided by this channel, which will be a demonstration of creating a basic ASP.NET MVC application on .NET 5. Right, let's create our code examples so that we can gain an understanding of attributes in C#. Let's create a .NET Core console application project. Let's name this project Attributes Examples. Let's ensure that we are using .NET 5 for this project. If you haven't yet installed .NET 5, please see a link below in the description where you are able to download the .NET 5 SDK. Note that you'll mostly be able to follow along even using earlier versions of .NET, but it is advisable to download .NET 5 to follow along with this tutorial and future tutorials. One of my core aims is to keep these tutorials right up to date. Please view a video created for this channel about the significance of the release of .NET 5. A link to this video can be found below in the description. So let's say that we wish to declare the assembly version global attribute in our code. We are able to do this by declaring this global attribute between the namespace declaration and the using directives. Okay, so why can't I see the assembly version attribute in the IntelliSense dropdown? The reason is that the assembly version attribute is part of the system.reflection namespace. So let's add a using directive to the system.reflection namespace. And now we are able to see the assembly version attribute along with other global attributes in the IntelliSense drop-down list. And we can now declare the global attribute against our assembly, like this. So here we are attempting to set our attribute version number to 2.0.1 through the declaration of the assembly version global attribute. Great, so let's see what happens when we attempt to compile the code. So we have a compile time error. Let's look at our error list to take a look at the details of this error. The description of the error is duplicate system.reflection.assembly version attribute. So let's double click on the error item in our list that is causing the compile time error to occur. Okay, so a new file is open and we can see a red squiggly line under the offending code. It is a file that has a name that contains the assembly name followed by the suffix .assembly.info, and we are able to find this file within our projects directory structure. And if we look at the comments within this file, it is clear that this file has been auto-generated. It's in fact been auto-generated by MS Build. Let's navigate to this URL to read a bit about MS Build. The Microsoft Build engine is a platform for building applications. This engine, which is also known as MS Build, provides an XML schema for a project file that controls how the build platform processes and builds software. Visual Studio uses MS Build, but MS Build doesn't depend on Visual Studio. By invoking msbuild.exe on your project or solution file, you can orchestrate and build products in environments where Visual Studio isn't installed. Visual Studio uses MS Build to load and build managed projects. The project files in Visual Studio .csproj, .vbproj, .vcxproj, and others contain MS Build XML code that executes when you build a project by using the IDE. Visual Studio projects import all the necessary settings and build processes to do typical development work. But you can extend or modify them from within Visual Studio or by using an XML editor. So the basic point I'm trying to make here is that many of these global attributes will be automatically declared in the assembly.info file when compiling your code using the Visual Studio IDE. You can gain access to some of these global attributes through the Visual Studio IDE. If you try to declare a global attribute, as I have attempted to here, you may get a compile time error because MS Build has automatically declared the global attribute in the assembly info file. As we have seen, this results in a duplication of the relevant global attribute declaration, which ultimately results in a compile time error occurring. You are able to declare certain global attributes in the way we tried to declare the assembly version attribute. For example, let's declare the assembly description attribute. Let's comment out the assembly version attribute declaration. Let's add our own assembly description metadata to our assembly through a declaration of the assembly description global attribute. Let's pass a value of myAssemblyDescription to the constructor of the assembly description attribute. Note that depending on how the relevant attribute has been written, when the developer declares an attribute, the developer is able to provide custom metadata to the relevant attribute through the attribute's exposed public properties or the relevant attribute's constructor parameters. So, we know that the purpose of attributes is so that we can add or modify metadata against certain program elements or even against the assembly itself. Note that attributes on their own do not change application behavior. The metadata provided through attribute declarations can be read at runtime through the use of reflection. Relevant metadata can then be evaluated by our code, and appropriate code logic can be invoked based on the declared metadata. So this is how the Microsoft Docs describes reflection. Reflection provides objects of type that describe assemblies, modules, and types. You can use reflection to dynamically create an instance of a type, bind the types to an existing object, or get the type from an existing object and invoke its methods or access its fields and properties. If you're using attributes in your code, reflection enables you to access them. Right, so let's use reflection to access and read certain metadata that has been added through the use of global attributes. So we need a using directive to the system.reflection namespace, which has already been included in our code. So let's write some code in our main method. Let's get a reference to the current assembly. We can do this by getting a reference to the program class's type and then assigning its assembly property value to a variable. We have named our variable thisAssemb, referring to the current assembly. We can then get the relevant assembly name by using the assembly reference stored in the thisAssemb variable and calling its getName method. And we can access the assembly's version information through the version property. Now we want to read the assembly's description, which should be the description that we included when we declared the assembly description global attribute. To get a reference to the assembly description attribute, we can call the getCustomAttributes method on the thisAssemb object and pass in the type of the attribute of interest to us. Note that we are using the typeOf method to get a reference to the object type of the relevant attribute. Remember, attributes in C# are objects at runtime. An object instantiated from the assembly description attribute class should be the first item in our object array. We can use the as operator to cast the object to the assembly description attribute type. If the casting operation fails, null will be returned. If the operation succeeds, an object of the assembly description attribute type is returned. Let's write code to write out the metadata information about the current assembly that we have been able to retrieve through reflection to the console screen. Let's run the code. Great! So we have looked at examples of global predefined attributes. Let's look at some general predefined attributes. Let's start with the conditional attribute. Let's first add a new standard library project to our solution And let's name our project Logging Component. Let's remove the automatically created class named Class1 and add a new class named Logging to our new project. Let's add a public static method to the logging class named log2screen. It contains one parameter named MSG and is defined as a string. The code for this method simply outputs the value referenced by the MSG argument to the console screen. Let's declare the conditional attribute against the log2screen program element. We have a red squiggly line because the conditional attribute is a member of the system.diagnostics namespace. So let's add a using directive to the system.diagnostics namespace. And now let's pass in an argument into the constructor of our conditional attribute. Let's pass in the text log_info. So what does log_info mean? Log_info is a piece of text that I've made up. This text represents a symbol in our code. We can use the define preprocessor directive and include the log_info symbol in our code. If the log_info symbol is defined using the preprocessor define directive within a file containing method calls to the log2screen method, the code within the log2screen method will be executed at runtime. However, if the predefined processor directive is not used to define the log_info symbol in the file where the log2screen method is called, its code will not be executed at runtime because we have used the conditional attribute to declare to the compiler that we would like this behavior to occur regarding the log2screen program element. So, the combination of the conditional attribute and the use of the define preprocessor directive can act like a switching mechanism, i.e. using this mechanism we are able to switch certain code on or off. This is especially useful for debugging purposes. If this is not clear, don't worry. We will demonstrate what is meant here through a code example. We are able to define our log_info symbol through the use of a preprocessor directive. We are going to use the define preprocessor directive for this purpose. Preprocessor identifiers are used to help in conditional compilation. If we navigate to this URL, we can see some of the preprocessor directives available in C#. For more information on preprocessor directives, please use this section of the Microsoft Docs as your guide. So here we have the hash define preprocessor directive that we can use to define a symbol in our code. So let's see how we can use a particular preprocessor directive in conjunction with the conditional attribute to conditionally output information to the console screen through our log2screen method. We must add our appropriate preprocessor directive code right at the top of our program.cs file in our code editors like this to implement the desired functionality. You can see we have the define preprocessor identifier in this line of code as well as the log_info symbol that we made up and passed as text to our conditional attribute which was declared against the log2screen program element. Let's include a using directive